Guys, in the last video we talked about buffers, and we said that buffers have to be made with weak acids and weak bases. We don't really know what those are yet, though, but we said they cannot be strong. They cannot be the strong acids, they cannot be the strong bases, and I told you that we're just going to have to memorize which one of these are strong. There's just no way around it. So, very often in a general chemistry course, what they talk about are acid disassociation constants. A lot of times these are given as a K for constant and a little a down here for acid. So Ka values is probably how you've seen these if you've taken a second semester general chemistry course. If you've not taken a second semester Gen Chem course, then be prepared because you're going to start to see these over and over and over and over. Well, Kb values are also out there. Those are base dissociation constants. So those are kind of the same thing. It's just in terms of a base instead of in terms of an acid. They can also treat this like H values. We can put a big P out in front. That means negative log. That's what the P means. We'll talk about pH in just a second. Well, we can negative log the Ka value, and we can negative log the Kb value. And what we end up with is a pKa and a pKb, just like pH. All right? So there's no difference there. That's just what the P represents. Anytime you see it, it represents negative log. All right, so acid dissociation constants. If these acid dissociation constants, Ka values, are very large, then that means that this substance is going to be classified as strong. It is not a weak acid. It is not a weak base. They want to get rid of it, and they want to get rid of it bad, and they don't want it back if it happens. All right, these are the rebellious teenagers, the problem children. When they turn 18, you got to kick them out of the house. You don't want them there anymore, right? Who knows what they're doing? But you kick them out of the house. They don't want them back. Once they're gone, they're gone. All the troubles go away. And now they're an adult and they can take care of themselves. They don't want those back. That is the definition of a strong acid and a strong base. Once they kick out the proton, or once they accept the proton, they're going to keep it away, or they're going to grab and hold on to it and not let it go away again in terms of a base. All right, so what are these acids and bases that have large dissociation constants? Large Kas and large Kbs. What are they? Well, there's a list, and here it is. If you look over to the left, these are your 6 strong acids, and if you look over to the right, these are your 6 strong bases. If it's not on this list, it's going to be classified as weak. Now, let's look over here to the strong acid category. Notice you have HCl, HBr, and HI. You also have HNO3. The N, the Cl, the Br, and the I are all located in the same general area of the periodic table. Look at it. If you don't believe me, take a look at their locations. The N, the Cl, the Br, and the I. All right, well, HClO4 perchloric acid is going to be added to the list. And H2SO4 is sulfuric acid, and that's also going to be added onto the list. So our 6 strong acids include perchloric acid, HClO4, hydrochloric acid, HCl, hydrobromic acid, HBr, hydroiodic acid, HI, nitric acid, HNO3, and sulfuric acid, H2SO4. Notice that in almost every single case, these are monoprotic. Monoprotic, mono means one, protic means hydrogen or proton. So one hydrogen, one hydrogen, one hydrogen, one hydrogen, one hydrogen, but Sulfuric acid kind of messes that up a little bit. And sulfuric acid is diprotic, which means it has 2 protons that it can give away. All right, so these are our 6 strong acids. If I'm not using one of these 6 in the laboratory, then I am using a weak acid by definition, meaning that that acid can spit off a proton, but that acid can also take the proton back in if needed. If one of these 6 gets rid of their protons, they don't want them back. These are the mean parents, right? You're out, you moved away, you're not coming back. The 6 strong bases are very similar. The strong bases include lithium hydroxide, LiOH, sodium hydroxide, NaOH, potassium hydroxide, KOH, calcium hydroxide, CaOH2, strontium hydroxide, SrOH2, and barium hydroxide, BaOH2. Again, look at the positions of the Li, Na, K, Ca, Sr, and Ba. You will find those very close to each other. So this will give you an idea of where all of the strong acids are located and all of the strong bases are located. What do the strong bases mean? Well, that means, definition of a base, it accepts a proton, right? So LiOH will accept a proton if it needs a home. But once it gets that proton, it doesn't really want it to leave. It will grab it, it will hold on to it for as long as it can before it is forcefully removed from the structure. Calcium hydroxide is the same way. If calcium hydroxide sees a proton and it reaches out and grabs it, it's going to keep it. As long as it can keep it, it will never really want it to go away. If this list, you're using a base and it's not on here, then that base is a weak acid, meaning that it can grab a proton, but it's just okay with it. If that proton needs to go away, it can go away. It doesn't need a lot of effort on your part to remove that proton once it grabs one. So this list is very important, and this list you've got to know. All right, the 6 strong acids, the 6 strong bases, you need to be able to regurgitate these back out onto a sheet of paper because these are important and they're going to keep creeping up more and more and more and more. Now, with that said, let's take a look at HF. What about hydrofluoric? Well, hydrofluoric is not on that list, right? Hydrofluoric is not on that list, so therefore it is classified as a weak acid. All right, CH3COOH, that's acetic acid. That was not on the list, so therefore this is a weak acid. What about magnesium hydroxide, MgOH2? All right, well, if I pull up that list for bases, you do not see MgOH2 listed, right? So MgOH2 is a base, but it is a very weak base. All of these would make good candidates to make a buffer out of, maybe. So this is what we have to do in the first step of preparing a buffer for a lab. We have to know what we can use and what we cannot use. We use preferably the weak acids and the weak bases when we make a buffer. If the acid or base is listed on this list, either to the left or to the right, I probably should not use that to make a buffer with. No strong acids, no strong bases. That means if someone tells me that I need to make a buffer with HBr, I'm going to laugh at them. I'm going to say, no, good luck with that. I'm not going to do it. If someone tells me you got to make a buffer with calcium hydroxide, CaOH2, again, I'm going to laugh and say, I'm not doing it. You can do it. Good luck with it. So why? Why are weak acids and weak bases, or why are preferred to make a buffer? Why should we not use the strong acids and bases? Well, let's finally give you a definition of a buffer. The definition of a buffer is to negate any positive or negative charge that might show up in solution. Okay, so let me put this in perspective. Let's say that we have a beaker, and this beaker has a buffer in it. And let's say that I'm working in a laboratory and I have added a couple of drops of a reagent. And let's say that this reagent is slightly acidic. There's no way around it. It's acidic. Well, maybe I do not want the pH of my solution to change. And if I'm adding an acid, my pH is going to change if I don't kill it out. Or if it's basic and I'm adding a basic reagent to the solution, it's going to change the pH. I've got to kill out all the alkalinity. And maybe I do not want my pH to change, and that's why I've got to do it. That's the purpose of the buffer. What happens is that if this reagent is acidic and it carries with it a proton, this proton is going to go in solution, and this proton needs to be killed out. I don't want my pH to change on me. So this buffer is made up of an acid and a base, but they have to be weak. And the reason is because if proton is added in, a little bit of base can go in and kill it out. Grab it temporarily. Maybe I need to use that proton eventually. I don't want to grab it permanently, but I just need to gate any of those changes that are taking place in my solution. Well, if this is a basic reagent and I'm adding that to the buffer, then I need to add a little bit of acid to that one, right? This buffer should have some weak acid that's swimming around in there, that's looking for some protons that it can basically give at the site of location. So that weak acid is going to neutralize any of the base that's showing up in the buffer. So overall, yeah, negate any positive or negative change that might show up in solution, but really a buffer is just a solution that keeps the pH constant. That's really what this boils down to. The problem with the strong acids and strong bases, I'm going to get violent reactions. These things can heat up. These things can steam. They could even explode. I don't really want that to happen, right? And then on top of that, when they grab a proton or when they give proton a home, they're not going to want to give it up. It completely changes the whole dynamic of the solution. Now I have something very stubborn that I'm going to have to go in and change and manipulate and modify to do what I need to do with it. The weak acids and bases, they're temporary. They reach out, they give proton a home, or they give a proton up. They do it temporarily to help things out for a little bit, but if it needs to go back to the way it came, then that's perfectly okay with them. That's why weak acids and bases are used. We need to keep the solution with a constant pH. We do not need to change the dynamic of the acid and the bases, though. So temporarily, these weak acids and weak bases will go in and allow our pH to stay constant. And then if we ever need those hydrogens ever again, they can be available for us to use, and we don't have to worry about doing funny things or difficult things in order for the strong acids and bases to give them back up. All right? So that's the purpose of a buffer. It keeps the solution constant in regards to pH. And it does that by comboing an acid and a base in the solution. But they have to be weak. That's the caveat there, right? They've got to be weak, which is okay. Most everything that we use in a laboratory is weak. Unless they show up on this list, strong acid and strong base, then it's fair game. I can use that to make a buffer with. So in the next video, we'll continue on with this discussion of a buffer. We'll eventually get to a point where we can talk about how to make one and a nice fancy little equation that we can use to make this a little bit easier to work with.